Welcome everybody. I will now stop video so we can focus on presentation. And I will talk, as Michael mentioned, about association rules. It's not 9,000, it's only 19 books so far. Otherwise, he told everything. I have only a couple of slides, and as you can imagine, there will be a lot of code, and I will develop association rules step by step in Transact.SQL, and then I will show you also R code and the algorithm in analysis services, how it is implemented, and also what you can do in Python and in Azure machine learning. So you will see many different ways how you can implement association rules. Now, first, we need to do a brief introduction, what I'm going to talk about, what kind of measures I will introduce. So association rules is the algorithm for market basket analysis. So we are searching for item set, combination of items that appear together multiple times in different transactions, that appear together in a single transaction over multiple transactions. So item is attribute value pair, right? And item set is combination of one item, two items, three items, or even more. Typically, we are focusing on item sets of size 2. The algorithm starts by scanning through the data set and trying to find item sets that tend to appear in many transactions. So it simply means we count how many times we get this combination of items and compare to the total number of rows or transactions. So here we have a simple example, the set of 5 rows, let's say 5 orders, and first one is frozen pizza, cola and milk, second milk and potato chips, and so on. And we define support as the number of rows with the item sets compared to the total number of rows. So this sounds extremely simple, and yes, it is. Association rules is not over complex algorithm. So the support can be expressed as an absolute number or as a relative number. So let's say a combination cola and frozen pizza appears twice, so we can just express support with an absolute number 2 or with a relative number proportion of transactions with this item set. 2 out of 5 is 0.4. Now this is item set. Cola, frozen pizza, the order is not important at this moment. Also, frozen pizza cola is also the same item set. But we want to talk about rules, and we try to express rules as if-then sentence. So if condition, then consequence. If customers purchase cola, then they will purchase frozen pizza. And support for this rule is 0.4. But this rule has an order. I can also change the order of items in this rule, and I can put frozen pizza to condition. If customers purchase frozen pizza, then they will purchase cola. The support for this rule is still 0.4. Is there any difference between these two sentences? Is one order better than another? Let's look at the combination milk potato chips. Milk potato chips, this combination appears once in 5 rows, so support is 0.2. Now let's try to express these rules. If milk, then potato chips, and also the opposite or turned around rule, if potato chips, then milk. Now look at these transactions again, more in detail. Milk appears in first, second, and third and fourth transaction. Potato chips appears only in second transaction. Basically, whenever potato chips is there, milk is also there. The opposite is not true. Whenever milk is there, it's not necessary that potato chips is also there. Milk is multiple times in the data set without potato chips. Therefore, seems like the rule, if customers purchase potato chips, then they will purchase milk, is somehow better than the opposite rule. If customers purchase milk, then they will purchase potato chips. How can we quantify this? We can calculate the confidence. Confidence is support for the combination, for the item set, divided by the support for the condition. Combination support is to 80% or 0.2, 1 of 5 transactions. Support for the rule, if customers purchase milk, support for the condition is 0.6. Milk is 3 times in 5 transactions. If we turn the rule around, then support for the condition if potato chips is only 0.2. So the confidence for the rule, if customers purchase milk, then they will purchase potato chips is 0.33, 20% divided by 60%. The rule that is turned around, if customers purchase potato chips, they will purchase milk, have confidence of 1 or 100%. So based on confidence, this rule is better. Now, should you always rely on confidence, or is it support that is better and so on? You know, the problem with association rules is that they are not so simple to interpret. They are simple to calculate, but they are not that simple to interpret. Support is, of course, important. Confidence is also important. Which one is more important? We can calculate additional measure, which is called lift, also sometimes called importance. So how do we calculate this? This is definition that lift is probability of combination divided by product of probabilities for both item sets individually. So if importance equals 1, both are actually independent. And if importance is greater than 1, they are positively correlated. Lower than 1, they can even be negatively correlated. Why? How could this happen? Well, we could have some combination that might has quite good support, but I don't have enough rows here. But let's say that milk, potato chips would appear twice, would have quite good support, 0.4. Yet on the other hand, milk alone and potato chips alone would appear 3 times more. Well, this means we would also have more transactions. Then the product of probabilities for each item would be greater than the product for the probability for the combination. So like 0.4 divided by, let's say, 0.9 multiplied by 0.8 is 0.72. So lift would actually be negative. Although support is quite high, it means that products are basically negatively associated. So there is third important measure. We have this support, confidence, lift, but we should also check other things. Maybe some product is always alone and so on. And finally, we can also define order. Sometimes order is not defined. Let's say in a retail store, order of products that were put in the basket is completely messed when you come to the cashier. Then you have completely different order, so you cannot rely on this order. But for internet sales, you can follow the order of products in the basket. So you can even define sequential association rules, which enforce particular ordering purchases. Order can be defined either with sequential number or with some date tag. So this is a little bit of theory. You see, it's not over complex. So let's go and start doing some calculations. So I will use AdventureWorks DW 2017 demo database. And for better performance, there are 2 pre-prepared views. I will just create permanent tables, so I will have less complex queries. And also I will index those tables, so I will have better performance. So here is what we have. We have line items where I have order number, and this is from internet sales, so I also have sequence, and I have model. So here we have this combination, Sport 100 with cycling cap, if we have item sets of 2 items. Sport 100 with row 350W and row 350W with cycling cap. And we have order. Cycling cap was in the basket before Sport 100. We could start analyzing immediately, but if we have some additional attributes in orders, like we have customer key, so we can get also some demographic data, we can even improve this analysis. Either we do association rules separately in subgroups, or we whatever we get, then pivot or group by these additional variables. So let's first check item sets where we have single item in the basket. So item sets of 1 item, not a single in the basket. So the most frequently sold item is Sport 100, then water bottle, then patch kit, and so on. Okay, this already tells me something. Now, next part is, remember that lift could be negative. Okay? We get some items that have negative overall impact. What does it mean, negative overall? These are items that are typically bought single, alone in a single order. So customers just come, take this product, and don't buy anything else. So if you are having internet sales, these are items you are afraid to see in the basket. But please understand again, we have to make this overview of data from multiple angles, because very frequent items might behave very well in combinations, but also be purchased multiple times alone. So what I will do, I will just calculate this items model. This is item, and calculate number of distinct orders and distinct items on this order grouped by customer key, and then calculating that count distinct, filtering count distinct order and model is 1. So we have single order. So you see if there one item in this order, because distinct order number will be just 1 and model also just 1. So let's check. And we see that water bottle is many times alone in its own order. So water bottle might also be a negative item. Please don't make any definite conclusions yet. Remember that this was very frequent item as well, sold in nearly 2,500 orders. So this count is, although it looks big, is actually relatively small. So you have to compare multiple results. Now I can also, since I have additional data, do pivot these results, let's say over region, and check where are these items. So water bottle is mostly sold alone in North America, not so problematic in Europe and Pacific region. Or let's see, by income group. So we are getting some information. This is additional analysis. This pivoting is not core association rules. Distribution over income groups doesn't have so typical spikes. We should now also check the frequencies of income groups. But as I said, I will not focus too much on this part, further analysis with further grouping and pivoting, which is not core association rules algorithm. Now let's find item sets with 2 models. So what I need to do is join my line items to themselves, this line items table to itself, based on equality on order number and non-equality. So model 1 is greater than model 2. And I will group by model 1, model 2, and count these rows with this combination. and say this is support. And I have the most popular item set is water bottle with mountain bottle cage and water bottle with road bottle cage. So you see water bottle goes very well with some other products. Now it's time for the next comment. Of course, you will say, normally that water bottle is sold with a bottle cage. Yes, this is another issue with association rules. You don't get a lot of information out of first most frequent item sets. This is something that you should usually already know. This is something very logical. And this is no surprise. And information is the same thing as surprise. If you are not surprised, there is no information there. So if you are not surprised by item set, water bottle, mountain bottle cage, you didn't learn anything. You already knew it. So it means no information here. And you see that even if we have great support, not a big deal. Okay, it's good enough for recommending system, but you didn't learn something what you didn't expect. Like, there was very known story in the past when they started doing association rules in some retail chain in USA. They found out very nice combination of diapers and beer, and they realized that mostly women were sending men to stores for diapers, and they put also beer in the basket many times. So this was a surprise. So this was a nice information. If you are checking this support and you are surprised immediately with first combination, second, third, don't be too happy. Usually it simply means something is wrong. Probably something wrong with your code data, or maybe you are a little bit weird and you are surprised with everything that is pretty common for other people. So the real information is somewhere lower, and this is the problem. You see, you have to look at this from different angles, because how much lower should you go before you find something really weird? Okay, for recommendation system, you don't even need to read this, but if you want to learn some weird combination that you didn't expect, you have to read a lot. Now I will create the same query in a different way. Instead of join, I will use cross apply. It's basically completely the same query written differently, but I prefer this. Also, the results are the same, right? Because it's logically the same query. I prefer this apply because it's somehow more natural how you add then third item, and if needed, fourth item with another apply in another common table expression. So it's somehow more intuitive how you build this. Please note that in some cases, in most of cases, apply will be implemented in an equal way as join, but in some cases, join might lead to different algorithms. So in some cases, join could be faster, apply cannot be faster. I think with apply, we can actually turn on execution plan and see what we get. With apply, you see, we do have some joins, right? And sometimes it has more options, SQL Server, to do joins with join algorithm or different joins. Let's check. In this case, I think I will get completely the same execution plan. Yes, 50-50 for two, right? Completely the same. But in general, SQL Server has more options with join than with apply. So apply cannot be faster than join, but sometimes can be slower. But I prefer how code is written. It's more clean how it is written. Now, when I added third item in the item set, it has to be greater than both of existing items. So now I could add the fourth item and just this where would be greater and greater. Now I will focus on those most useful item sets, pairs, two items in item set. I will calculate this support, but I will express models as a rule, if, then. And I changed the where condition from greater, I changed to this different. So I will get both combinations, model 1 and model 2. So every item set will be twice in the result. So I have water bottle, mountain bottle cage, and I have mountain bottle cage, water bottle. And in both cases, support is 993. So why did I do this? You can imagine immediately why did I do this? Because now I can calculate confidence. So I have if then rule, now I can calculate confidence. So next step, let's add confidence. So I'm checking all pairs, I create rules, and then I count distinct order number for model 1. So this is support for the condition. And now I can calculate confidence by dividing support for the combination by the support for the condition. And then I can calculate percentages by also using the total number of transactions. So I'm just counting distinct order number. I'm using cross join here instead of additional common table expression, because with common table expressions I want to follow the flow of the development of the algorithm, and this is not really important for the flow. So I just and cross join of a single row is actually efficient. It's just adding a column to the result. So let's calculate confidence. And now I can also order by different terms. So I have support, and I calculated support in percentage, and I calculate confidence. So support in percentage is support divided by number of orders. Now I see mountain bottle cage, water bottle has the same support as water bottle, mountain bottle cage, but look at the confidence. So first rule has much higher confidence than second. So people apparently first buy bottle cage and then bottle. And this is also quite common. Now let's develop this a little bit further and let's add lift. So I'm calculating again all possible pairs, expressing the rules, calculating support for the condition, then calculating support in percentage. I get count of distinct orders with cross join, calculating confidence, and now I'm simply calculating probability. So support for the item set divided by number of orders, and then divided with probability for the model 1, support for the model 1 divided by orders, multiplied with probability for model 2, right? And now I will order this by lift and then by confidence. Now I can do many different ordering. And you see the query is still pretty efficient, right? So now I can see interesting thing. Turing tire and Turing tire tube have this combination have very huge lift. So if one is there, second will be there practically very strongly. And I have confidence for the first Turing tire, and then Turing tire tube is much bigger than confidence for the second. And this one here we have very low lift. Here we don't have negative lift, but this is lower than 1. So it means this patch kit has negative influence on long sleeve logo jersey, but please don't support any support that is too lower than, let's say, 20 cases makes no sense. So it would make sense to filter this. Now we can also order by, let's say, first by support, then confidence, check with different orders. So we can view these association rules with in many different ways. So this one with big support has also quite good lift, so apparently it's a good rule. Mountain tire tube Sport 100, you see it has big support, but apparently it is more like coincidence. Quite huge support. Confidence, even the bigger one is not that good one. Lift is much lower. And here we have already negative lift, water bottle Sport 100. So support is still high, confidence is even lower, and lift is already negative. So you see, we already get some interesting information. Now, next thing I can do is sequence. So how do I include sequence? So I will find all combinations, but include that line number in the table from the left is lower than line number from the right. And now I have sequential rules. I will just use support and confidence without lift. And sequential rules, you see, this sequence is pretty important. Mountain tire tube Sport 100. This sequence has high support, but not so big confidence. Sequence mountain bottle cage water bottle is also having high support, but also high confidence. So if somebody puts mountain bottle cage in basket, you should immediately suggest also water bottle. This one again, remember this one has also negative lift. So if there is water bottle in the basket, you shouldn't recommend Sport 100 because although the combination appears multiple times, remember these two products are very frequent. These are two most frequent products. So even more times they appear without the second one in the pair. Okay, what else could you do? Let's say you could additionally even improve this, but I will not do it at this moment. You could add two virtual products in each order, begin of sequence with, let's say, line number 0 and end of sequence with line number higher than any line number in this sequence. And then find this sequence, do this sequential analysis again, and look which product is usually right after begin. So on the left would be begin, right? So this is typically the product that starts the shopping sequence. If multiple times would be end of sequence at the end, this is also a dangerous product, means that people usually stop shopping sequence after this product is in the basket. So basically, you see, with some more or less complex queries, I don't find these queries, I know it also matters on your experience with programming, especially in Transact SQL, but I don't find them over complex when they are written this way with common table expressions, apply operator. It's very simple to follow the logic, and you see there is basically no mystery in association rules. Now, of course, if you use more specialized languages and tools, you get this black box. But now we know how this black box is working. So let me start with good old analysis services, multidimensional data mining. You see, for this association rules, we have a very nice algorithm. For this association rules, you define transactions with one side table. So I have orders, and then line items are included as nested table here. So analysis services multidimensional supports nested tables. So this all line items are then treated as a single column inside this orders table. It's not joining, it's just like adding items to a single column. So this is not normalized model anymore. You cannot, let's say, export this directly to SQL Server or even to analysis services tabula. And here is my mining model, and I simply defined the order number as the key, and line items are this, what are we predicting, and also model is the key. And then I can also set some parameters, algorithm parameters. So, for example, support 1% is minimum, and probability, this is confidence, 0.1, 10% is minimum. For some reason, I don't know why, but for some reason, Microsoft used with analysis services multidimensional somehow their own naming. So probability is actually confidence, and lift is called importance in analysis services. But there is one very, very nice thing here, and this is this great viewer. This will be the best graphical presentation. I don't need to redeploy the model. I just need, or I need to, no, I don't need to redeploy the model. So analysis services multidimensional have great viewers that also help you a lot in understanding what you get also for other algorithms. Although this data mining is not used a lot anymore, it is still a very nice entrance to this world, because, you know, not everybody will become R or Python developer in order to do 2 or 3 not too complex analysis. This is one thing. Here you do everything with clicks, but then of course it means you are pretty limited, and great visualizations. So first visualization is showing you probability, which is support in this case, expressed by percentage, and importance, which is lift. Okay, this needs to be extended a lot to get also the numbers. So this is also the lift. And here we can see maybe at the end we have even some, you see, red, negative even numbers. But this is because Microsoft uses for importance logarithms. It also uses logarithms, so values that are lower than 1 are then shown as negative numbers. Here you can say filter. Let's filter first. Let's show only attribute name, not existing. So I have only these combinations, right? And then let's say filter a rule, right? So we can even use character filters. So for example, mountain. And okay, I have some special character before mountain. Okay, so here are only rules that have product with something on mountain. Now, this is maximum rows. I can also define what is the minimum support. I want to show minimum importance, so I can filter the rules. Here is view on item sets. Again, I will show attribute name only, and minimum item set size. It starts with 1. So of course the most popular is port 100. Remember, we did this analysis also in Transact SQL, and then it's water bottle. So we can say show me minimum size of 2, and then I have mountain bottle cage, water bottle, and so on. But this is just minimal size. So somewhere here we have first item set of 3 items here, item set of 3 items, mountain bottle cage, mountain 200, water bottle. And this is the best viewer, association rules viewer. Sorry, this is the viewer, dependency network viewer, the 3rd tab, clicked on wrong tab. So here, let me also lower this, show attribute name only. Here you can see how these things are connected, and you can immediately see that port 100 is connected to many articles, so it's very important. Cyclic cap might be also important product because it's somehow transitional product. It brings you additional products in the basket. A road tire tube is also quite important, also another transitional product. So this is very, very nice, and you can even find only most important links, so you get less cluttered picture. Patch kit is extremely nice, goes in combinations with other products. So although very old, also this analysis services, multidimensional data mining can still be very useful, helps understanding the rules a lot. Maybe you can understand them graphically better than with Transact SQL results. And generic content reviewer is showing you these rules, how they are stored and what are attributes. So you see, this is basically a row in a table in analysis services, which has nested column for node distribution. So this is for ML road tire tube. Now enough of analysis services. Let's show another option. So we have nice package A rules. Let's load it. I already installed it. And let's load library ODBC and read my line items. So these are my line items now as a data frame. I have already executed this code. So I have also saved this code, this result in a CSV file. So it's very easy to import CSV file in Azure ML. So I will not do it again. Now I need to define transactions. So I will split model over all the numbers and call these transactions. So now I am creating specific object transactions based on my data frame. Now I can check the transactions. So I have 13,006 transactions. This is the number of orders, maximally 37 items are all distinct items. So this is an example of a couple of transactions. So order SO61381 as Fender set, mountain, and Sport 100. This one has 3 products. Now let's see size of this transaction. So we have 2 items, 3 items, 3 items. Now in this A rules library, I have this a priori function that is calculating association rules. And this is parameter is list minimum length. I use search for rules at least of minimum length 3 and minimal support and minimal confidence. Let's calculate this. And let's use inspect to have output of these rules. I have a little bit too big font. So I have rule, support, confidence, and lift, and count. However, these rules are at this moment not sorted. These are not sorted, but I see all these measures, support, confidence, support as count, and also lift. Now I have nice function eclap, which can help me finding most important item sets. So this is only 40 most important item sets, and they are here not sorted by support, but I can see support expressed as probability and proportion and as count. Now I can, for example, search with top n function. I can search for top 10 items. And these are top 10 items, single item. We already know Sport 100, water bottle, and so on. Now I can use sort function and inspect first few rules by, can I move this a bit? Now I should lower the font, I guess. I would like to get everything in a single row. Here, appearance. Let's make this font a little bit smaller. Now it remembered. Yes, let's try to inspect them again. Sorted by confidence. Yes, now I have everything. I can even, in a single row, I can even enlarge this a bit. So you will be able to see it better. Let's try with 14. 16 was just a bit too big. So let's execute this again. Yes, we still have everything in a single row. Then I can sort by lift and find them. And this is sorted by lift. And you see completely the same results as in SQL Server. Now, A rules. This is library that overloads the plot, and we can get different plots. So this one is very similar to the plot I got viewer in analysis services. It's very informative. So color is based on lift. So here is this lift 12. And then size is based on support. So I can again easily spot the most important rules. Now I can also find left side and right side. So I will check what is on the left side, whatever on the right side is Sport 100. Let's find this, which products lead to Sport 100. So these are not sorted, but four most important rules. Road tire tube Sport 100. By support, this one, mountain tire tube Sport 100 is the most important. And the opposite, where Sport 100 is on the left side, which rules are on the right side, road tire tube, mountain 200, mountain tire tube. Great. Now we have three options, which all of them were great. Now we are going to not so great options. So I am switching for Python. I'm not saying, of course, that Python is bad for data science, but Python is behind for data science, behind R. Now, Python was developed even a year before R, but it is a general language, and only in last few years went also to data science area. And when it goes to data science area, it is actually copying things from R, implementing things from R. So we also get this concept of data frame and matrix calculations. However, matrix calculations and data frames are built in core R. So we have overloaded operators, like multiplication works also on matrices, or also logical operators. In Python, by default, we don't have these overloaded operators. So we must import pandas, first NumPy library. This one brings overloading operators also for matrix operations. And otherwise you have to do things in loops. And then pandas is built on the top of NumPy and brings data frame. Now, most of algorithms that you have in Python are in scikit-learn library, which is using pandas data frame. So it's efficient. And then we have Microsoft implementations, for example, RevoScale and Microsoft ML libraries, which also have many functions that work on pandas data frame and are efficient. Unfortunately, I don't know any Python library for association rules that will use this pandas library. So I'm defining transactions as an object called list. And this is simple copy paste of first 10 transactions from SQL Server. I think I have this code? So here, yes, here it is. So this is it. So I just get top 10 as a single long, this is a list, and I'm creating a list of lists, a list of products. And now I can use a priori algorithm from a priori library to create rules. And then I can extract rules, and immediately I need to use loops. And let's extract the rules. Now here are the rules: left-hand side, right-hand side, and so on. Support, confidence, lift, And I'm working only with a couple of rows. How many rows? 10 input transactions, so really not very useful. Now let me check this. Let me show you the simple performance test. So I'm importing NumPy library, creating some, I will create some random numbers. First, I'm creating a function that will actually do calculation of reciprocal values of inputs with a loop, with a for loop. Okay, so let me just execute this part. Function is created. Now I'm creating 1 million random values. And now I will also import timer, so I will be able to measure time. And I will compute reciprocal values with my function and measure the time. So million values, it was nearly 2.5 seconds. Let's copy this. Now immediately when I imported NumPy, the division operator, divide operator was overloaded with matrix operation. So let's use now this overloaded and look at this. This is the performance difference. Now let's do the calculation, and you see it was more than 50 times faster with NumPy, and unfortunately without these matrix operations, Python this association rules is practically useless because it can work really on small data sets only, and even these data sets must be converted to a list. Hopefully we will get better algorithm in Python. We are extremely close to the end. We have one more thing, Azure ML. How is association rules implemented in Azure machine learning? It's not implemented. It's so simple, but I'm not done yet. I made a simple experiment. So I imported my data set, right? And then what I used is simply R script. So at least I can execute R and Python script. And of course, I will not use Python script. And I already executed it. So I can visualize this also in Azure ML. So I have, you see, first information about general, how it was specified, confidence, minimum value, and so on. And then here are a few most important rules. So we have support and confidence as percentage. This is what I calculated. Also lift. Again, it is split. And I also used this visualization from R. So this was probably the simplest. Conclusion, you can do very well association rules in Transact SQL. Great is still great implementation is in analysis services. Very good implementation in R, not so good in Python, and no implementation in Azure ML. So we are coming to the end. Let's see, I have here one question. Question is, what other scenarios or industries could the association rule algorithm be applied in other than sales transactions? Okay, this, I will just show you something. I will just show you something. Here, some code. And I will show you here how I'm using these rules. So I'm using this association rules algorithm also for text mining, for example. What does it mean? I used full text indexes, and then there are some functions with full text search. There are some nice functions. For example, sysdm fts index keyword by document. You can actually read the full text index, which terms were extracted, and then I can check which terms appear frequently together. So this is one example. Of course, there is really depends only on your imagination. You can use this in many other ways. Okay. Any other questions, comments?
Yeah, we have. So I'll kick off the questions that we've got listed for you. So question number one, the analysis on basket transactions are sales that are actually made, but would it also be useful to track an individual's journey to get to a specific sold basket? For instance, if they have added a sharp knife and then may have added an apple, then a banana, and then replace them with an orange, we could maybe deduce to recommend an orange over a banana or apple for future baskets with a knife.
Wow, yes, this could be interesting, but this means you would replace based on some property of the product that is known to you, based on some context. So I guess if you would have some way how you could define that knife goes better with banana than with orange, then yes, I guess.
Good. So could we implement a single or a triple item set for enhancing accuracy of the support? So if we do like milk is a 0.6 probability of buying, for instance, would that make sense? Or even adding 4 or 5 item sets to get the better and more accurate support?
Well, think of this context. If we are people, right? If you are measuring people, then think of how we behave when we come to the market. Not frequently we know, let's say, what things we need to buy together in advance. Many times we just buy an item and then we remember, why don't we put also this in the basket? And this is what you are searching for. If you have too many combinations, then it means, too many items, too big item sets, then it typically means that person planned in advance. So this person maybe went to shop in IKEA, right? This is what is known to you from Sweden, right? And then you must know exactly what kind of nuts and bolts and everything you will purchase. So you plan it in advance. So I would say, although you would get more accurate numbers, you would get less information because there wouldn't be much surprise in it. But as I said, yes, it's worth trying. There is never-ending story. It's worth trying. So might be useful in some other scenarios which don't come to my mind at the moment.
So as the size of the number of transactions or data grows, the probabilities and support changes. Are there any useful reasons to historically track these changing probabilities over time?
Definitely, great question. Definitely, it makes sense. So you could even store these results. Let's say with SQL, it would be easy to store these results in some kind of simple data warehouse. So you would store these results in a fact table and then time of analysis and then timetable. So yes, this would be really useful. So you can check how patterns change over time.
Cool. So you showed a lot of algorithms and ways to get information, but the question is, do the algorithms get old? Or can I with confidence use, for instance, the SSAS data mining thing, even if the data mining is not so very updated and modern anymore?
Well, association rules is not a complex algorithm. So basically, it is not developing much in any language. It should develop more in Python to include more efficient way of computing. But otherwise, you see, we get still completely the same result. So this is pretty simple algorithm. So I guess it will be safe to use it also in next few years, also with analysis services.
Perfect. So I think Mark's last question.
Okay, well, let's try and make it a good one then. So would it be a good idea to also track associations for other more abstract basket item properties such as cost or even color or size of items, or even track the purchase context such as who is actually buying the items?
Definitely. You see, I only have shown initially few these possibilities by splitting data over income groups, over region. But yes, definitely, it would make sense to also check this in different ways, like with you mentioned cost. So maybe separately which more expensive products are purchased together, which cheaper, or which combinations, one more, one less expensive, are frequently purchased together. Definitely any kind of demographic could be useful. Also might be useful to use aggregations or categorizations like product taxonomy, subcategories, categories, especially in retail stores. What do I mean here? You could create analysis that would do some drill down. So in a retail store, in a retail chain, you might have hundreds of thousands of different products. So you might have billions of combinations. And this is impossible to make an overview. So you can start, let's say, to check which categories of products are frequently bought together. And then you see, okay, these are these two categories that are frequently bought together. And then you expand one to subcategories. And then you pick a subcategory and expand second to subcategories. And this way you drill down and calculate association rules step by step, because otherwise it's impossible to simply make an overview of billions and billions of rules.
Well, I guess that concludes the question session, and I would say thanks for joining us, and a big thanks to Dejan.
Yes, and a big thanks from my side also to hosts and to everybody that joined us today.